Hi, Bobby.
Hi, Aniruddhan. So maybe we'll just scan through what we discussed in the
I think it's a good idea
yeah.
because this is a lot of analysis, no?
Correct.
So we need to make sure that students understand it really well.
Yes. So in fact, we were looking at some way to get a transfer function for the circuit.
Correct. So
the
for
linear
any
system.
input,
Yes.
we want to find out what the output is.
Yes.
Correct.
So you said we can, if we can represent this in a Laplace domain,
Correct.
input can be in the Laplace
Yes.
and then get the output in the Laplace, take the Laplace.
Take the Laplace inverse.
So otherwise we would have written the differential equation and so on.
That's right.
So from there we reached this transfer function.
Correct.
That was clear. Then
That
we
was
took an example. Yeah.
That's right.
Then we discussed about the impulse response.
That is correct.
Something,
That is correct.
the response itself gives the information about the
That is
system.
correct. That is correct. So because if you apply an impulse at the input,
Yes.
right, in the frequency domain that is just one,
Correct.
right?
Correct.
So the output will be the transfer function itself.
Itself.
So the response is that to an impulse is the transfer function.
Yes.
The time domain small h of t was the impulse response. Correct.
So that's the beauty of impulse
That's right.
signal itself.
That's right. And students will be seeing this again and again in signal processing,
Yes.
right? In
yes.
signals and systems and DSP and so on.
Correct. Then we also said we can represent in pole zero form.
Correct.
Because if we know the roots, we can represent that way. From there, we moved on to Bode plot.
That's correct. We said that there is a scientist called H.W. Bode
Yes.
who came up with a very nice way of plotting
Yeah.
the transfer function magnitude and phase.
And phase.
This is very useful, right, in a practical sense,
Correct.
to learn so many things about the system.
Exactly. Just by looking at the plot, a lot of things can be
Correct.
understood.
Correct.
So we actually took this low pass filter, and then we found the transfer function is this.
Correct.
We have set S equal to j omega.
Correct. That is very important because we are interested in the steady state.
Yes.
You apply a sinusoidal input, what happens?
Yes.
S is very good for both transient when you turn on a switch,
Exactly.
as well as what happens when you apply a sinusoid.
Exactly. So then we found it's 1 plus 1 by j omega c, and the magnitude of this is represented in this fashion.
Correct.
So while we were plotting this, we were saying that, if one is very large compared to omega RC,
Correct.
then the magnitude of h of j omega is just 1 itself.
Correct.
And 20 log 1 became 0.
Correct.
That is why we have this in this fashion.
Correct.
And this also means omega is very low compared to
1 over RC.
1 over RC.
Correct. So the RC time constant is the inverse of this point of the Bode corner point.
Yes.
Right?
Yes.
Okay.
Yes.
Okay.
So the other case we discussed is if omega RC is very large compared to 1.
Correct.
So that means omega is very large compared to 1 by RC.
Perfect.
So essentially we are looking at the condition where this term becomes 1, correct?
Yes.
So that's the point where we have this
The Bode corner point.
Bode corner point happens.
Correct.
And then correspondingly we said there is a phase plot. So where omega equal to 1 by RC, you have minus 45 degree in this case.
In this case.
Because this is a pole.
That is correct.
Then we said if it's a pole, every pole will introduce like this. And if it's a 0, it will be plus 45 degree at the 0 location and so on.
That's right. That's right. And you can have a pole or a 0. The 0 might actually add phase. The pole may subtract phase. You can also have other cases as well, no?
Yes.
You can have poles, because here it is minus 45 degrees.
Correct.
Because it is 1 by 1 plus j omega RC.
Yes. Yeah. Then we took an example like this, where we have h of s equal to this, and then the magnitude we have written in this fashion. Again, we have looked at for omega very less compared to
100.
100, we have this total magnitude in dB equal to 20 log
20. Correct.
20. So that's a constant till 100, omega equal to 100.
Correct.
After that, we could write 20 log 20 plus,
Yes, 20 log 20 plus 20 log omega by 100.
yes,
Correct.
yes. So that we have written it as a single term here.
Correct. That's right.
So actually it will be sum of these two terms, correct, no?
That is true.
So the first term due to the 20
Correct.
log 20, and the second term due to this one.
Correct.
And those two we are just adding, and we put the characteristic like this.
Correct.
Now maybe we will take even simpler example,
Sure.
just to revise because it's new for the, right?
I agree.
Yes.
It will reinforce their learning, no?
Yes, yes.
Correct.
Yes. So let's say I have maybe h of s just a constant. Okay.
Ah, okay. So no poles, no zeros.
No zero.
Okay.
Like
Okay.
an amplifier which has gain through, constant gain for all frequencies.
Correct. Correct.
So then our magnitude plot will be,
Or in fact, it's like an amplifier.
yeah,
Or you apply a voltage across the resistor and you're plotting the current.
exactly.
Right?
Exactly.
That is also going to be
Exactly.
no poles, no zeros.
Yeah. Something which is not frequency dependent.
Correct.
So here actually we have then, so we used to write magnitude of h in dB.
Correct.
So the corresponding value will be
Correct.
just 20
Log k.
10 k.
Correct. So normally the first step for h of s is to convert to h of j omega.
Yes.
But here there is no s at all.
Yes.
So there is no,
Yes.
it is exactly the same. No
Yes.
step to be done.
Yes.
Correct.
Yes. So yeah, h of j omega
Is also k.
is also k. Of course, we mentioned the x-axis is in log scale,
Is in log scale.
like 10 and so on. Maybe they should look at log scale, how it looks. It's a bit difficult to draw here.
I know, that's right. It's quite difficult to draw.
Yes.
It's very non-linear,
Yes,
right?
yes.
Correct. They will see the scales, the grid.
Yeah,
There will be a lot of space between 1 and it will be 1, maybe 2, 3, 4.
Correct.
There will be a lot of space between 1
Yes,
and 2,
yes.
and then slightly smaller space and
Yes.
so on.
because 10 to 100 is accommodated here in
Correct.
a log fashion.
Correct. Correct.
So, and anyway, phase for this is 0, no phase.
That's right.
Now, on the other hand, let's take another simple example. Let's say h of s is k and j omega.
You mean k times s?
Sorry.
Ah, okay.
K times s
K times s. Okay.
means h of j omega is k times
J omega.
j omega.
Okay.
So now there is a frequency dependent component,
That's right.
correct?
That's right.
So what will be our, so the 20 log 10
Of k times j omega, no?
k times j omega or k
Magnitude, no? K times omega.
k times omega.
So once you take the magnitude, it will be k times omega.
Yes.
Correct. So you'll get two components, no?
Yeah.
20 log k,
K.
and 20 log omega.
Yes.
Maybe we'll draw both components.
Yeah. So let's say 20 log k is somewhere here.
So that is constant,
Yeah.
just like the earlier case, no?
Yeah.
It is just constant.
And
20 log omega in this dB versus log scale, it will be a straight line,
Yeah.
correct?
Yeah. So it will be so when omega equal to 0,
When omega equal to 0, it will be at minus infinity, no?
correct.
So we can't show it here.
Correct.
So maybe what we can show easily is when omega equal to 1.
Equal to 1. So in the log scale,
At 1 it will be 0 dB.
yes.
Correct?
Yes.
That 20 log omega.
Correct.
Correct.
So this will be something passing through.
That's correct.
1, and it will increase. I mean, let's say if omega increases 10 times, your amount will be increased by
20 dB.
Yeah.
Correct.
Yeah. So basically log 1,
Correct.
sorry, log 10,
Log 10,
which gives 1,
which gives
and
you
then
1.
20.
Correct.
So this is plus 20 dB per decade.
Correct.
So the resulting one will be,
So resulting one, normally we just straighten out the corners. We saw this yesterday.
Yeah.
The approximate way of drawing it is to just show with the corners.
Correct.
So till the two curves cross, it will be 20 log k. After, sorry, it will be 20 log k constant. After that, it will go up at 20 dB per decade. Is that correct?
But this is there throughout, no?
Correct. So one way to make an approximation is that, let us say, below the point where they cross, we will just approximate it to the higher curve. Is that allowed?
See, if it was a 0, like s plus some
Correct. That is true.
z,
Yes.
then we can do that.
Then you can do that. Here you cannot do that. Correct.
So this means this curve is there always.
Always.
For all frequencies.
That's
You were
correct.
saying it will go to minus infinity.
Minus
no?
infinity. Correct.
So
Correct.
which means just summation of these
Summation of these two is what you should do.
Correct.
Correct.
So in that case, I mean corresponding to 1, the value will be here.
That's correct.
Correct, no?
That's correct.
So there are many plots. Now students
We'll
will
show
be-
it like that. Correct.
Students will be confused.
Correct.
So this is this.
Correct. Perfect. So the whole thing is just shifted up by 20 log k.
Or if k was not there, I mean k was 1,
It will just be 20
then
log
it would have
omega.
been,
The original one.
this we have discussed actually.
This we have discussed yesterday.
Yes,
Correct.
Yes.
So the one, if you had a 0 only, it would do like that.
Correct.
Correct?
Correct.
You have some 1 plus s by z or s plus z, something
Correct,
like that.
Correct. Yeah. So maybe we should take slightly complicated example.
Yes. Sure.
So
Maybe something with some poles also.
poles and
Sure.
zeros.
Sure.
So do you want to suggest?
Okay. So maybe we'll take something with 1, 0 and 2 poles. Okay. So maybe I'll have something here I have
Yeah.
written down.
Yeah.
So let's say h of s is 2000
Okay.
into s plus 0.5
0.5.
divided by,
Yeah.
let me do one thing. I'll put in 3 poles. Okay. So s into s plus 10
Okay.
into s plus 50.
Okay. So there are 2 poles here, and then there is another,
There is another pole at the.
like we have taken j omega.
That's correct.
Yeah. Also, that reminds me, for the previous one, we did not draw the phase plot.
We did not draw the phase plot. Correct. We should.
So the phase here will be
90 degrees, no?
yes,
Always.
because in j omega we know it
It
will
was the
be,
j omega.
Yeah.
Correct.
So it's a 90-degree throughout for
Correct.
all frequencies. So we are not plotting that. No need to plot.
No
that.
need to plot it,
Yeah.
I think.
So
And normally, if you have something like this, normally the systems people, control systems people, or circuits people might say you have a pole at the origin.
yeah.
You don't have a 0, or rather in this case, not a pole but a 0
Yeah.
at the origin.
Yes.
right?
Yes.
If you had written it as k into s plus z,
Yeah.
z would be 0.
Yes. Exactly.
Correct?
Exactly. So the phase plot, it's obvious. I mean,
It's obvious.
at plus 90 degree.
Correct. And here that reminded me, because now here you have an s, standalone
Yeah.
s, no?
Yeah.
You can write it as s plus 0 if you want.
Correct.
So it is a pole
Yeah.
at the origin.
Understood. So now this we may have to rewrite into some fashion, no?
Correct.
Because if you look at our explanation, oh, where is that? Here
Yes.
we have written it as 1 plus j omega.
J
RC
omega RC, correct. We need to bring it to that
in
same
that
form. That's true.
And this corner frequency was happening at 1 by RC.
That is correct.
So ideally, we would like to have 1 plus form.
That's correct.
Correct?
Correct.
So it should be 1 plus s and a constant.
Correct. So maybe, so what we want is in a general form,
Yeah.
we will write it as some, maybe we can write it down.
Yeah.
We will write it as some gain A
Yeah.
times the general form of any h of s
Yeah.
can be brought to some A into 1 plus s, in this case, some A into 1 plus s by z,
Z1.
z1 by, let us say in this case, s, we can write it as s
Yes.
into 1 plus s by p1 or p2 if you want, because there is one p1 implied, no?
Yeah.
1 into 1 by p1, 1 by p2 into 1 plus s by p3, some form like this.
Yeah.
This is the standardized form.
Correct.
So gain times 1 plus s by z1 into 1 plus s by z2 and so on,
Yes.
divided by 1 plus s by p1 into 1 plus s by p2 and so on.
So this clearly says where the pole occurs.
Correct. You can
Correct.
immediately
So
see it.
confusion is
Correct.
not there.
And the gain is also known
Yes.
directly. A.
Yes. Yes. So we need to bring it in that form.
Correct.
That means, so 2000. So I need to multiply by 2,
Correct.
or
Correct.
we'll just bring 0.5.
We'll bring
outside.
0.5 out. So you
Yeah.
can you can multiply this by 0.5.
Yeah. So that will be
1 plus s by
plus
0.5.
S by 0.5 divided by s.
Correct.
Then I need to bring in 10 outside.
Correct.
So that means 1 plus s by 10,
Correct.
and then again
You'll bring 50
1
outside.
plus s by 50.
Correct. Correct.
So some of the zeros we can cancel maybe.
Correct. 20 into 0.5.
Correct? Huh?
Okay. So
Any mistake?
let me just check. So 20 into 0.5 by 5.
Yeah.
So 20 into
0.5 is 10.
Correct. 2.
By 5, 2.
2. Correct.
So 2 into 1 plus s by 0.5 s into 1 plus s by 10, 1 plus s by 50.
Correct.
So the 0 is at 0.5.
Correct.
There is a pole at origin. That is this one. you are
Correct.
mentioning.
Correct.
Then another pole at 10,
10.
another pole at 50.
50. Correct. And there is a constant gain of 2.
2.
Right? That also we have to take into account.
So
So first we'll write it in j omega.
exactly. This we have only formed the h of s
Correct.
in this form.
That's right.
Okay. So h of j omega two into 1 plus j omega by 0.5 1 plus j omega by 10 into 1 plus j omega by 50.
Correct.
In fact, we can take individual terms separately also. in the
Correct.
sense.
We can plot each one just like we did for
Yes.
k times j omega,
Yes,
no?
yes.
For the part 2,
Yeah.
for example 2.
So
we
maybe
can
I'll
do the
take
same
it
thing.
into a fresh page.
Yes.
So basically this 0, I think we mark it as Z1.
Correct.
This will, I mean,
At
it
point,
starts at 0.5.
correct. So,
So from there it will go at plus 20 dB
plus
per
20
decade.
dB per decade. Correct.
So i- if you assume I am drawing
Yes.
in magnitude form, it will be something like this.
Correct.
So this will be at 0.5
Correct.
plus 20 dB per
Correct.
decade.
Correct.
Then the P1
Yes. P1 is at origin.
origin.
So right from 0, you will
Yeah.
see going down, magnitude going
Yes,
down
yes.
at 20 dB, minus 20 dB per decade.
So it's a pole, so it will be minus 20 dB per
Correct.
decade.
Correct.
And this will go through at 1, it will be
At 1, it will be 0 dB.
0 dB.
Correct. Correct.
P2, it will start activating only from 10.
That is
Until
true.
that it will be 0.
Correct.
Or what we are saying is, until that 1 is much higher than this. Correct.
Correct.
So log 1 is 0, which we have discussed earlier.
That's right.
So this will be, sorry, something going till 10,
Correct.
0 dB,
Correct.
then
And
at
minus 20
minus
dB per
20
decade. Correct. Correct. So let's do one thing. This P1, no, because we have shown 0.5 here.
Yeah.
We'll either move this a little bit to the left or move it so that in students' minds, no,
Correct.
we will
I
draw
agree.
it somewhat
I agree.
to scale.
I agree.
Maybe the first one we can move to the left. It may be easier. Or move both to the right. Perfect. Correct. But that's enough. It's anyway log scale, no?
Yeah.
So we can't move it too much.
Yeah.
Just a little bit.
Yeah. Yeah.
Sure.
Okay. Then P2, P3
Ah,
starts at 50.
starts at 50.
So 10 means maybe 50.
Yeah, in
somewhere
log
here.
scale, it will be somewhere there. Yeah,
Yes.
let's say.
So until 50 it is 0.
Minus 20 dB per decade.
Yeah.
Yes. And 50, no? We'll mark it there.
Yes.
Perfect. One thing we forgot.
Ah.
20 log 2.
Yes.
Constant.
Yes. Important.
Yes.
Silent person. there.
Yes.
So this 2 will just give 20 log 2.
That is 6 dB.
Yeah. So that will be a constant throughout.
Correct. Perfect.
So now just addition of all this.
Correct.
Correct, no?
Correct. The big difference between a pole and just adding these things, you are adding all of these in dB.
Yeah.
So if you go to the previous page, they should not, the whole curve shifted, one more page, the whole curve shifted up, no?
Yeah.
Because you are adding them in dB.
Correct.
This is not like a 0 where you can just approximate the corner frequency and do it, no?
Yeah.
So they have to shift curves if they are adding constant values and so
Yes.
on.
Yes.
That is important.
Yes.
Like you pointed out, you have to add everywhere.
Correct.
In all
Correct.
ranges,
Correct.
not
Correct.
just, you can't approximate saying below this it is small and so
Yeah.
on.
Yeah.
Hmm?
Yeah.
Correct.
Basically, our multiplication, sorry, became addition,
Became addition.
and the division became subtraction because in the
Inside the log.
Yes.
Because students may not be comfortable with dB, this 20 log of something.
Yeah.
So they need to keep that in mind.
yeah, because the dB term itself may be new.
That's right. That's right. They may have heard it in audio.
Yeah.
So many decibels is very common.
Correct, correct.
Nowadays, even in the newspaper, you hear this jet engine went past, it had so many decibels
correct,
of
correct.
sound.
That's true. So I'll maybe try to draw here itself.
Sure.
So magnitude of h dB. It may not be that straightforward to draw unless we have a.
That's true. Correct. Correct. So let's
approximately
see.
we can draw it.
Approximately we can draw. So let's take a guess. Okay. So this 6 dB is going to be there everywhere.
Yeah.
So let me go to very, very small frequencies.
Ah.
Frequencies much below 0.5.
Yeah.
Let us start with that. That's easy.
Yeah.
If you go to frequencies much smaller than 0.5,
Only
Z,
this will be there.
only P1 and this 2.
Correct.
So it should look like 2 by j omega,
Okay. Okay.
right? So this 2 will also be there.
Or if we look at 1.
That is the best point.
That may
Correct.
be.
Correct.
So let's say at 1.
So problem is at 1 the effect of Z1 will also be there.
Oh, because it's 0.5.
It's at 0.5.
I didn't see that.
Yes.
So then we should consider 0.5 first.
Exactly. So below 0.5 we can draw it.
Correct. So 0.5 may be somewhere here.
Yeah. Yeah. Correct.
Yeah. So below 0.5.
So below 0.5,
This was 0 dB.
correct.
In that place, 6 dB will be.
6 dB will be there. Correct.
Slightly higher.
No, it should be like this, I guess. Oh, you're trying to draw this one?
Huh?
Okay. So it will be this plus P1. So you'll get actually a minus 20 dB per.
P1 I missed. So we need to add these 3 at this
Correct.
point.
So at 0.5, instead of being 0 dB, it will be 6 dB. Correct?
Correct. Correct. So 0.5, 6 dB will be there, plus the contribution due to
that.
this.
Correct.
So from this,
You can go upwards.
yeah. So this value will be 6 dB? No.
No, it's not. This value will actually be 20 log 1 by 0.5.
Correct.
It will be 20 log 2,
Yeah.
isn't it?
Yeah.
So most likely at 0.5 it will be 12 dB.
Okay. Okay. We will look for the shape only.
Yes.
Because exact
Correct.
drawing will be difficult. I think.
Correct. I think we also don't have space here.
Yes. Yes.
So
this portion will be minus 20 dB due to this.
correct.
Am I correct?
Correct.
Because that is there for all frequencies.
That's right. So the easiest way to find out the y-axis values, like you pointed out, no, at 1, this value goes to 0 dB,
Yeah.
P1.
Correct.
You will only have the contribution from 6 dB.
6 dB and
Of course, if you did not have the 0.
yeah, correct.
So if you extrapolate this curve,
Correct.
right?
Correct.
So that's how you know at 0.5 it should be 12 dB,
Yes.
right? But
Yes.
yeah, so
Yes.
what you're saying is correct.
So this was going at minus 20 dB,
Correct.
but at 0.5,
Yes.
there is a 0 which is going at plus 20 dB.
Correct. So now
These two will get,
we'll cancel each other out. Correct.
so from here it has
Should
to
be flat.
a flat
Yes.
till 1.
Correct. Well, even beyond 1, right? Because you have to hit the next pole. So,
So there is no pole at
there
1.
is no pole at 1.
Till 10.
Till 10, it has to be flat. Perfect.
Yeah. Yeah.
Correct, no?
Yeah, correct. Then at 10 we have minus 20 dB per decade. going
Correct.
now. So that means this will start going at minus 20 dB.
Correct. You're adding a constant value to something that is going at minus 20 dB per decade.
Yes.
So it will start going at minus 20 dB per decade.
And at 50 there is one more pole.
That is true. So I understand. So it should start falling even faster,
Correct.
because you'll have almost like 1 over omega squared.
Yeah.
So minus 40 dB per
So
decade.
one more minus 20 comes.
Correct. So maybe minus 40 dB per
Minus
decade.
40 dB per decade.
Correct. So because it's 1 over omega squared,
Yeah.
if you go to 10 times higher frequency, the magnitude will fall by 100 times. 20 log of minus 100 is minus 40 dB. Correct.
Also, the h of j omega will look like this.
Will look like this.
The
Correct.
magnitude.
Correct.
So where it will cross 0 dB.
Yes.
Huh?
Yes. It's going to be a little bit hard because here it is at 6 dB, no?
Correct. Or even
No,
slightly higher.
Even higher actually,
12.
to 12 dB.
Yeah.
Because 12 dB.
Yeah.
And then it starts going down, no? From 10 to 50, 5 times, for 20 dB for 10x, 5x will be 14 dB. So it will cross, before it hits 50, it will cross 0 dB, looks like.
Okay.
Just a high level calculation
Yeah.
seems to show that it will cross
Yeah.
before 50.
So that may not work. Oh, it's working.
No, it's working. Good, good, good.
So before crossing 50.
Correct. I think something like that is good.
Okay.
Correct. Perfect.
Hmm.
So you are basically saying 0 dB point. You were
Yeah.
just marking 0
Yeah.
dB there.
Yeah.
Correct. Oh, by the way, one more thing I wanted to ask. See, you have the x-axis marking is not going down till 0 because you are plotting in dB.
Yeah.
So this can actually extend. Y-axis is wherever you start plotting.
Correct.
If you want, you can extend it below also.
Correct.
Because minus infinity, you have to go in log scale.
Yeah.
You cannot even show it on the paper.
Yes.
Right? So I have seen some textbooks even plotting below the
Beyond that.
beyond the y-axis point.
So actually, if we have a log plot,
Yes.
then even we can, calculate these values and put down there what it is.
That's right.
So from there go minus 20 dB.
Correct.
Correct?
Correct.
Yeah.
That's right.
So from there it will be flat. Again, draw at minus 20 dB. So this crossing point, etc., will automatically happen.
That's right.
Now we have made a lot of
Approximations in our drawing.
Yeah.
In our drawing.
So we were driving in a very slippery road. I would say.
Well, it is hard to draw everything to scale.
Correct. Correct.
You can draw approximately to scale.
Correct.
Otherwise, you take a log graph paper.
Yeah.
You will get it exactly.
Yes. So I think students need not worry
Yes.
that drawing this will be so complicated.
Correct. Correct.
Yeah. Okay, phase plot, maybe I will skip.
Okay.
Huh?
I think so.
Yeah.
But I think they should understand that it's relatively straightforward.
Yes.
Just like we did for the magnitude, no?
Yeah.
They can do the same thing for
We
the
can do
phase.
that. Yeah.
Right?
Yeah.
So at the pole frequency or zero frequency, it will add either plus 45 or minus 45,
Yes.
depending on two things, no? Whether it's a zero or a pole,
Correct.
and whether it's a positive pole or a negative pole.
Yeah.
Right?
Yeah. Because these two are nearby, 10 and 50.
It's a little bit more complicated to
By
draw.
hand drawing, it will be a bit difficult.
It's difficult. Correct.
But what we know is j omega will introduce
90 degrees. Minus 90 degrees.
90 degree.
Correct.
The second pole will introduce another minus 45 at that location.
Correct.
So
And
some of these will be present there.
correct. So normally the phase curves, it will go as a curve
Yes.
depending on the contribution from each one.
Yes.
I think they will learn to do this in a more detailed manner in the control systems
system
course. That's correct.
Yeah. So, but if you want to write an expression, maybe we can do that.
Yes, that we can.
So, the phi will be, the numerator will be,
Yeah, plus tan inverse omega 2 omega.
yeah.
You can just write it as 2 omega.
Then
Minus
we have 90 due to this,
minus 90
minus
degrees.
due to this.
Correct.
Then we have another minus tan inverse
omega by 10
and another,
tan inverse omega by 50. That is in fact another advantage of writing the h of j omega in this form.
yes, yes.
You just take the coefficient of the imaginary of j, that will give you the phase directly.
Correct. So, this could be plotted, but hand drawing, I think it's a bit complicated.
Little bit difficult.
Yes.
Correct.
But students could try at home.
Yes.
Or maybe just using an Excel.
That is true.
Compute
They can
this
compute this and
omega and
calculate
see how it comes.
Correct. Because there will be two things where the curve will be a little bit hard to plot on
Yes,
paper.
yes.
One is this 0.5 and 1, they are
One,
very close.
yeah.
And the other one is this 10 and 50. Correct. Especially 10 and 50 is going to be hard.
Yes, yes. But I think overall we have an idea.
We have a good idea.
If a transfer function is given, how to draw the magnitude in dB
Correct.
and phase in dB.
That's right.